Hello, welcome to discussion 1. We'll be going over question 1, asymptotics and limits. So before we start this question, feel free to pause this video, take a look at these two notes, and attempt these questions yourself. We'll be going over these questions right now. So before I start this question, I do want to briefly go over that in order for f of n to be O of g of n, f of n has to be upper bounded by the growth of g of n. So because g of n grows faster, this number will diverge and grow faster and dominate f of n, which is why the limit converges to 0. I do want to make a point that in this class, for the most part, we'll be using big O instead of theta. The reason for that is that not all algorithms that we cover in this class can be represented in theta notation. I'll give you an example of the algorithm quicksort. In quicksort, it's amortized O of n or n log n for the most part. However, in the worst case scenario, the runtime is n squared. So we're not able to give a tight theta bound for quicksort, which is why we result using big O. So with that in mind, let's go over question 1a. Prove that n cubed is big O of n to the power 4. We can use this asymptotic limit rule over here. Let's just directly apply the limit. So f of n over g of n equals the limit as n approaches infinity of n cubed over n to the power 4. Let's divide n cubed on both sides. So we get 1 over n, and then we know this converges to 0. So that means that n cubed is O of n to the power 4. Awesome. Let's move on to 1b. Find an f of n, g of n greater than 0, such that f of n is O of g of n, yet the limit is not 0. So with that in mind, I do want to point you to this rule. So f of n is theta of g of n if f of n is O of g of n and g of n is O of f of n. So if we come up with two functions with a theta bound, then we're able to have, as you can see here, a limit that is not 0. It is some constant c, but still satisfies this O boundary. So I'm gonna come up with something pretty simple. Let's have f of n be a runtime of 3n and g of n be a runtime of 5n. And then let's apply the limit like we always do. We don't even need the limit actually. So it's just 3 over 5, which is equal to some constant c greater than 0, which implies that f of n is theta. Oops, not sure what's going on here. Let me, man, that is unlucky. Let me get rid of that. Okay, sorry about that. F of n is theta g of n, which also then applies that f of n is O of g of n. Awesome. So that's question 1b. Let's look at question 1c. Prove that for any constant greater than 0, we have log n is O of n to the power of c. So I guess the significance of this question is that, like, let's say n is like some really small number, like 0.1. This is still, log n is still upper bounded by this this function. So that's pretty significant, and we want to prove that. So let's do what we've been always doing, applying the limit. And then I am kind of stuck here because in these previous problems we've been doing, we've been having really simple simplifications, like dividing by n on both sides. In this case, we're not able to, so we'll be using the hint, applying L'Hopital's rule. We know that both of these limits are approaching infinity as n is approaching infinity. So then let's go ahead and apply L'Hopital's. We know that the derivative of log n is 1 over n, and then we apply just the power rule, c minus 1, for the remainder, or the quotient. And then let's simplify this again. 1 over c n c. And then this is growing at the rate and diverges to infinity. So we know that this is 0. So we've showed that log n is O of n to the power of c. Cool. The last question here, find an f of n, g of n greater than 0, such that f of n is O of g of n, yet the limit does not exist. In this case, we would be unable to use limits to prove that f of n is O of g of n. I do want you to pause this video and try this out for yourself. To guide you in the right direction, I do want to point something out before you try it yourself. So I want you to take a look at this trigonomic function. The limit of sine of n as n approaches infinity, we know does not exist, because sine of n alternates between the range of like -1 and 1, which is why the limit does not exist. So as you come up with your solution, try to incorporate sine of n into your solution and see where that gets you. Okay, I'm gonna assume you paused the video, so let's go ahead and start the question. F of n, g of n. So I do want to incorporate sine of n, so let's put that in f of n. And then with f of n, a problem that we have is sine of n has a range of -1 to 1. And I don't know of a function with a negative runtime. That would be kind of crazy. So what we'll do is we'll add 1 to sine of n so that our runtime will never be negative. And then I will slap on an x here, and you'll see why later. For g of n, I do want to think of some possible functions. So let's say x is, or g of n is, we're not using x, sorry about that. Let me change these variables really quick. Let's say g of n is n to the power of 100. So even though we're using sine of n here, if we were to apply the limit rule, sine n plus 1, we can see that g of n dominates f of n. So like we can simplify this even further, and the limit does exist. So think about what would g of n be, and I will give you the answer in 3, 2, 1. Let's say, ooh, I already erased it too quickly, but g of n is n, and let's see why that's the case, or why that's like a solution, one of the solutions for this question. So we're not able to use the limit, however, we're able to use another property that we saw in the beginning of the worksheet. So let's take a look at this property right here. So for something to be O of g of n, f of n is bounded by g of n times some constant. So let's try to fulfill this property. Ooh, that is weird. Okay, yeah, sorry about that. Let's try to fulfill this property and to solve this question. So we know that f of n has to be less than or equal to some constant times g of n. So let's write everything down. Okay, so we can cross out the n's on both sides, and we have sine of n plus 1 is less than or equal to c. We know that sine of n has a range of -1 to 1. So that means that the largest value that the left-hand side can be is 2. So if we apply constant equals 2, then f of n will always be less than or equal to 2 times g of n, which then means that f of n equals O of g of n. Awesome. That was question 1. Well, let's move on to question 2. This is question 2, asymptotics, complexity comparisons. A. Order the following functions so that all of ij, if I comes before fj, in the order that fi equals O of fj. Do not justify your answers. So go ahead and try to solve this problem yourself. I'll go ahead and explain my thinking right now. So this is very generalized, but we can classify functions into a couple of cases. We know that constant time functions are faster than logarithmic functions, which is faster than polynomial functions, which is faster than exponential functions. So these are very general classes. Obviously, you can have a function that is both polynomial and logarithmic, like n log n. However, for the sake of this question, this should just do. And let's first put all of these functions into their respective bins. So let's look at them one by one. We have 3 of n. So f of 1 is 3 to the power of n, which is exponential. F of 2, is n to the power of 1 over 3, which is a polynomial time function. F of 3 is 12, and that's a constant value. F of 4 is a bit tricky. However, if you remember your log laws, this will just evaluate to n. So f of 4 is n. F of 5 is square root of n, which is still a polynomial time function. I do want to simplify and put it in a notation that will be easier for us to compare these functions later on. Exponential. F of 7 is logarithmic. And then f of 8 is a bit hard. However, we're still having n to the power of some value, so it's growing at an exponential rate. And then f of 9 is n to the power of 3. Okay, awesome. So now that we have each function in their respective classes, let's go ahead and put them in a more specific order. So, sorry about that. So we know that constant times are faster, so f of 3 has to be first, and then there's only one item in the log. And then let's take a look at the polynomials. When we look at polynomials, we ignore constants. In this case, none of these functions have constants. So let's ignore those, or let's not even consider them. And let's just look at the powers. Let's take the smallest power, and that will be the fastest function. So that's n to the square root of n, which is n to the power of 5. And then n to the power of 4, or sorry about that, n to the power of 2, actually. 5, 4, and then 9. And then let's take a look at these exponential functions. So the slowest one is f of 8 f sub 8, and then 6 f sub 1. So these are the functions in terms of fastest to slowest. Let's take a look at 2b. In each of the following, indicate whether f is O of g or omega g, or both, in which case it's theta g. So for the most part, we'll be applying these rules, asymptotic limit rules, to help us solve this question. However, we're able to use a couple of tricks that we'll see later on in this video, and that'll be pretty useful when you do some asymptotic analysis of your own. So bi, log base 3 of n, log base 4 of n. Attempt these problems yourself before continuing on in this video, but let's go ahead and start with bi. So as we take the limit of n approaching infinity, I can modify these functions a bit. So I know that log base 3 of n is the same as ln of n over ln of 3. They're the same bases. I put the ln of 3 on the bottom so that it's the same as log base 3 of n. And then we can represent ln base 4 the same way. This evaluates to 1 to 4, 3 times ln n over ln n. I can cross these out, and what we get is some constant term c, which means that this is omega. Awesome. B2, n log to the times n to the power 4, n squared times log n to the power 3. Let's also take the limit as well, and then we can apply a couple of log laws to help us simplify this question or expression. So we can pull the powers in front, so we have 4n log n over 3n squared log n. We can cross these out, ignore constants, cancel out the n, and we have the limit of 1 over n, and that equals 0. So that is big O. Oops, that is B2. B3, square root of n and log n to the power 3. So what we saw earlier is that polynomials dominate logarithms no matter what, so that we know that this is a omega bound. If you want to attempt this problem more rigorously, I recommend doing what we did in question 1c, where we applied L'Hopital's and found that I guess both of these converge to infinity on both sides, so we applied L'Hopital's. So if you want to do a more rigorous version of this proof, go ahead and do that on your own. However, we just need to briefly justify our answers. So poly dominates log. Finally, B4, n log n and n plus log n squared. I want you to take a wild guess and think to yourself what this solution would be. 3, 2, 1. The solution is that it's theta. So the reason for that is that similar to the reasoning before in B3, the polynomials, in this case n, dominate the logarithm expressions. So if you remember in 61b, we can cancel these, or we can just ignore these expressions, the logarithmic expressions, and just look at n because they dominate. And then obviously n over n equals to 1, so this is a theta bound. That was question 2. Moving on to question 3. This is question 3, Hadamard matrices. The Hadamard matrices H0, H1, H2 are defined as follows. H0 is the 1 by 1 matrix 1, and for k greater than 0, Hk is the 2 power k to the power k matrix as shown here. So let's interesting. Okay, so let's attempt this. Feel free to attempt this question on your own. Try to get as far as you can. However, let's get started. So h of 0, as we're given in the base case right here, is just a 1 by 1 matrix. And then h of 1, this is a recursive function or definition of matrices. So let's take a look. So h of 1, this little top left is just h of k minus 1, which is 0, or h of 0, which is 1. Same as these two quadrants, as well as we take the negative here. So that's h of 1. H of 2 is, let's take a look at this. So okay, so this is h of 2. That was question 1a. Basically, we just take a look at these little quadrants and then apply the recursive definition of the matrix. 3b, compute the matrix vector product h2 times v, where h2 is the Hadamard matrix you found above. Let's just do a bit of matrix multiplication then. And 1 minus minus 1, minus 1, 1, minus 1, 1, minus 1, and then 1, 1, 1, 1. Awesome. And this equals 0, 0, 0, 4. That was 3b. Now 3c. Now we will compute another inequality, or another quantity. Take v1 and v2 to be the top and bottom halves of v respectively. Therefore, we have v1 and v2 equals, if we stack the matrices on top, v1, so the top half is v1 and the bottom half is v2. We see that we have the same value. We just broke it down into a top and bottom portion. So it says it wants us to compute u1 and u2, where u1 is h1 v1 plus v2 and u2 is h1 v1 minus v2. So let's go ahead and do that. So u1 equals 1, 1, 1, negative 1 times v1 plus v2. So let's add these two together and add these two together. And this is just the 0 vector. So we know that the matrix will be 1, 1, oh, we know that the result will just be the 0 vector as well. u2 is 1 minus 1, so 1 plus 1, and then minus 1, minus 1. So that's 2 and negative 2. And what do we get? We get 0, 4. So it says stack u1 and u2 together to get the vector u of length 4. So u is 0, 0, 0, 4. What I notice about u is v1 and v2 is basically this. However, we get the same result actually. This is foreshadowing for the next question, or next part of the question. But if you can see here, we basically broke down our matrix into this top half and bottom half. And the cool thing is that we only needed to do math on this little left quadrant of the matrix. So we forego all this multiplication, and that's really cool. We'll see further down in the question how much runtime this will save us in the end. So let's go ahead and continue on with the question. Suppose that v is a column vector of length n equals 2 to the power of k. v1 and v2 are the top and bottom half of the vector respectively. Therefore, they're each vectors of length n over 2, basically the top half and bottom half. Write the matrix vector product, hkv, in terms of hkv minus 1, or v1 and v2. And since hk is an n by n matrix, v is a vector of length n, the result will be a vector of length n. Go ahead and try this problem out on your own and come back when you're done. But basically, we steal a lot of the work that we've done in the first half. So hk of v is the same as hk of v1 times v2. How can we break this down even further? We know that the definition of hk is hk minus 1, negative hk minus 1, v1, v2. And then feel free to finish this question if you know how, but let's just expand this out. So hk minus 1 times v1 plus hk minus 1 plus, oh, those are not supposed to be pluses. We multiply the vectors together, or the matrix with the vector. hk minus 1, I hope I'm making that clear, sorry about that. And then let's take a look at the bottom row, hk minus 1 v1 minus hk minus 1 v2. Awesome. Finally, v1 plus v2 V1 minus V2. So we arrived at exactly what we had here. Awesome. So that's our expression in terms of these terms. All right, let's start question 3E. Use the result from C to come up with the divide and conquer algorithm to calculate the matrix product of HK times V, and show can be calculated using n log n operations. Assume that all numbers involved are small enough such that basic arithmetic operations take unit time. So let's take a look at the result of C. We know that we got U1 and U2 from H of 1 and H of 2. And then let's also take a look at 3D. In 3D, we found that H of K of V is H of K minus 1 V1 plus V2 over H of K minus 1 V1 minus V2. So let's begin with our algorithm. For 3E, let's break down the vector V into components V1 and V2. And then we'll do what we did in D and evaluate H of K minus 1 V1 plus V2 and H of K minus 1 V1 minus V2. And then we apply this definition recursively until we hit our base case, which is H of 0, in which case it's the 1-by-1 matrix. So this divide and conquer algorithm breaks down the problem into its subproblems, right? In this case, our subproblem is H of K minus 1 V1 plus V2 and H of K minus 1 V1 minus V2. And then once evaluated, V equals V1 over V2. Or sorry, not V1 over V2, but K minus 1, V1 plus V2, V1 minus V2. So basically we stack these vectors together until we form our solution. And that's the basis of our solution. Let's take a look at its runtime. So I'm not sure if this was covered in mini lecture. However, we'll be using the recurrence relation to evaluate the runtime. So the recurrence relation takes the format of something that looks like this. This looks probably like a bunch of jargon if you're looking at this for the first time. However, sorry about that. However, I'll briefly go over it. So the basis of divide and conquer algorithms is that we take subproblems and combine these subproblems into a unified solution. So let's take a look at this term A. A is the number of subproblems. So num subproblems. B is the number of subproblems, or how we break down the subproblem, size of the subproblem. And then finally, D is the time to bring these subproblems together, or the time to evaluate the current level. So let's go through the recurrence relation for 3E. So in A, we have two subproblems, right? We have to evaluate H of K minus 1 using the vector V1 plus V2, and we also have to evaluate K minus 1 with V1 minus V2. So the number of subproblems is 2. T n over B, the size of the subproblem is broken down in half because the size of the matrix H of K minus 1 is half of the size of the matrix H of K. So the size of the subproblem is broken in half, so B equals 2. And then finally, what is the runtime of the current level? I want you to think deeply about this. And this will give you a really this will really like point out any flaws in your understanding of the recurrence relation. So I guess, okay, with that time, the runtime or the value of d is 1. The reason for that is for this subproblem, we have to evaluate v1 plus v2. If you recall, the size of v1 and v2 is size of n over 2, so we're adding two size of n over 2 vectors, and that's O of n over 2 time, which we can call O of n. So O of n is n to the power of 1, which is why d is 1. So hopefully that recurrence relation explanation / walkthrough made a bit of sense. We can then apply Master's theorem. There are a ton of different ways to do Master's theorem. The way I like to do it is see what this evaluates to. In this case, 2 is equal to 2 to the power of 1, which implies that the algorithm is theta n to the power of d log n, which is the same as n to the power of n log n, because n to the power of 1. But you can probably just look up Master's theorem on Google Images, and there's like a ton of different ways to do it. Do whatever makes the most intuitive sense to you. Speaking of intuition, I do want to briefly cover the recurrence relation tree, because recurrence relations are essentially geometric sums, and I feel like having a understanding of how it looks visually would help understand or give a deeper understanding to this question. So this is what the tree would kind of look like. Number 2, boom, 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 and then all the way to the base case. So these trees hopefully look familiar if you took 61B, but basically the top level is T of n, right? And in T of n, we have a runtime of, for the current level, which is n to the power of 1, or just linear time. And then we break down T of n into 2 subproblems, size n over 2. If we had 3 subproblems, I would draw another tree, but in this case, it's a really cool, beautiful binary tree of size n over 2. And if we add these 2 expressions up, the runtime of the 2 levels of n over 2 is also n. And then you can imagine I fill in the gaps here. We have n over 4, and then adding all of these values up, we also have a runtime of n for all of the 4 inputs of size n over 4. And then we just continue on building this tree, and we can see that we have n plus n plus n. And how many times do we have n plus n plus n to get our total runtime? It's log n times, because we're having the size n until we hit 0, or not 0, 1, which is our base case, which is the 1 by 1 matrix. And having by 2 is this, until we hit 1 is the same as logarithm, right? Log is the number of times we multiply something until we get some value, which is like kind of the same as having something until we hit 1. So the total runtime would be theta n log n. Okay, this got kind of messy, but hopefully that little brief side tangent was really helpful. We'll be moving on to question 4.